I think they said you can go whenever you're ready.
I can go?
Yes, you can.
Okay, thank you. So first of all, thank you organizers for inviting me to this wonderful conference and giving me the opportunity to speak here. I want to start by, I want to start from the beginning. A few estimates. If I don't know anything about the subject, how would I start? So chromatin fiber is a polymer, and many speakers refer to it as a polymer, sort of pretending then it's clear to everybody what is polymer and what is polymer physics and so on. I'm not sure it is exactly right. So let's try. This is the length of a linear chain in base pairs. And the first number that you may want to know is how to translate this length in base pairs into the length in centimeters. You need to know density, how many base pairs per nanometer is there. And this density is surprisingly not known very well. It's within a factor of 3 or so, this number of base pairs per nanometer. Depends on how many nucleosomes you have and so on. So this translates into contour length of about 10 centimeters. Then, if you know polymer physics, you realize that then the main question is flexibility. In native flexibility of this fiber, how flexible it is. We know that flexibility of double helical DNA corresponds to persistence length of 50 nanometers, and persistence length of 10 nanometer fibers is not smaller. So Kuhn segment is greater than 100 nanometers, although it's not known very well. The diameter of this object is 10 nanometer, which is why it's called 10 nanometer fiber, and it is an important unitless quantity, diameter divided by this effective straight segment. This number is small. And this is very important for many things that, for instance, Professor Spakovich was talking about. It's super important. It determines the role of close interaction between nucleosomes versus interaction with the mean field of other nucleosomes around. So volume fraction, how dense is this object? If you estimate volume fraction as I will show in the next slide, perhaps it's about 10%. So in terms of polymers, it means it is a so-called semi-dilute polymer system. It means it is sufficiently dilute, it's much less than 1, volume fraction is much less than 1, but it is still very much an interacting system. It is what Dejean called a semi-dilute system. And then there are a few more comments about mesh size, charges, and other things. So perhaps I should mention, because that will not go into my subsequent slides. I want to comment on something that was discussed this morning in Professor Sharp's lecture about this phase segregation, and specifically about specificity of phase segregation. When specificity is usually discussed, it is discussed normally in terms of contrast of some interaction energies. Like in Professor Spakovich's lecture, he mentioned that it's only 1.5 kT of difference in energies. And then he emphasized that there is amplification due to polymerization effect. When you are talking about non-equilibrium phase segregation, there is something else that I wanted to emphasize, and I didn't prepare the slide for it because it is my reaction to this morning's session. there is something else. There is an additional specificity which comes from purely non-equilibrium considerations. It's not the issue of energy, interaction energy. And this comes for the following reason. You can think of these non-equilibrium effects, actively ATP-driven effects, as the effects of local violation of Einstein relation between essentially friction coefficient, or the size of diffusing particle and its diffusion coefficient. You can think of activity as enhanced diffusion, enhanced contrary to what normal physics would imply. And then this gives you another leverage for sensitive phase segregation. You may not be sensitive or specific in terms of energies, but you may be specific for a different reason. And we have some more, I should say, we, in this case, it means Jean-François Jany and myself, we have some model in which we can explain some effects like that. Okay, so I promised to return to the volume fraction. Here is the estimate of volume fraction of chromatins in the nucleus. And there is an important consequence to it. We can also estimate mesh size. It is estimated right here. And the mesh size of this chromatin mesh turns out to be on the order of 100 nanometers, which is on the same order as persistence length or Kuhn-Seidel. That means the mass that you are looking at inside chromatin is something like this, in which every mesh, every interval between chains is basically separated by pieces which are more or less straight. It's not coiled parts. It's the pieces which are more or less straight. This is also an important part. Now, as regards charges, it's not very popular subject in chromatin discussions, but in fact, it is there because all nucleosome bodies are very, very, very highly charged. And if you draw experience from other biological systems, such as viruses, in virus case, DNA or RNA in this case for this particular virus can absorb twice as many charges as RNA itself has, and there is some explanation for it. So charges are also important. Now, important thing for chromatin is hydrodynamics. Hydrodynamics, it's a long-range effect, and it's long-ranged in the same way as Coulomb forces are long-ranged, and they are screened. There is strong screening of hydrodynamic effect, and there is a simple physics which explains it. If you think about, let's say, some set of obstacles and you pump liquid past it, then liquid does not penetrate very much in between the obstacles. So that's hydrodynamic screening. Now, entanglements is something that is rather popular, and one can ask, what is the entanglement length? Entanglement length is something that was introduced by Dejean as in normal polymers, it's an average distance between two neighboring entanglements. It's actually a deceptively simple concept. It seems very simple because every speaker and every teacher explains it by a gesture. Entanglement is like this. That was to emphasize the point. So what I want really to say is that entanglement is not quite like this, as my pictures show, because clearly this seems to be an entanglement. This doesn't seem to be an entanglement, but if you imagine that there is another piece over there, then there is already entanglement between these brown and blue loops. So what is entanglement? It is not a two-body property, not a two-piece property, but a multiple-piece property. Nevertheless, there is a quantity called entanglement length, and it is a useful quantity to measure. It was measured for chromatin by Rosa and Everard in their simulation, and the result is not very well defined, but it is the best we can do at this point. It's between 4 kilobase pairs and about 1,000. Between 4 and 1,000, it reminds me an error bar of some of our astrophysics colleagues. But that's where we are. And this is very important quantity, because if you believe that you have many topo enzymes, and they act very actively, and they are productive, as in famous Sikharov and Janink model, then you may want to know how many of them you need and how many of them work. On the other hand, if you believe that they are not very active and you have topologically constrained polymers, then its properties are such as the ones which you referred to at the end of your talk, are controlled by this parameter. Okay, so let me skip this. I also want to point out, in this climate and in this weather, it's probably not very relevant, but everyone knows, everyone probably sometimes wears a sweater, and sweater is a set of so-called slip knots. Slip knots are something that is actually observed in proteins in another biological system. These objects here, they are not knots, because if you pull the ends, they go away. But they are interesting slip knots. And the question whether slip knots exist or do not exist in chromatin is a super interesting question, I think. Because these slip knots can form interesting structures in some polymers and so on. So now going forward, I want to mention a theorem which was proven by my student, former student Jan Smrek. He was inspired by mathematical history of various studies of various space filling curves, starting from Peano and Hilbert in the end of the 19th century. And Jan Smrek, my student, was also inspired by Escher drawings. And he was able to prove essentially the following statement. If you are given a high C signal, then the theorem says that you can construct a space filling curve which will produce this high C signal. Okay? So the question which remains open in this regard is the following. Suppose you are given a high C signal and you view this as a macro parameter in your statistical mechanics description. What is the entropy which corresponds to this macro state? In other words, how many actual polymer conformations exist which correspond to the given high C map? I don't have answer to the question, and nobody does, which is why I probably will skip that. But I want to mention that in a related question, there is an active discussion about the idea of topological glass. So the idea of topological glass is related to the slip knots and sweaters. And sweater is, well, if it's well done, then it's a long-lived state of a polymer. We hope, when we buy a new sweater, we hope that it will live long. So in this sense, some people, some of them are listed here. Matthew Turner is the leader of this group. They say there might be this glassy state in this related to penetration of the loops, and it's very much an open question. In this regard, I am very much excited about this new paper by Bintu and company, where they went beyond high C, and this way, I hope, the question of slip knots and the question of entropy of high C maps and so on can be addressed eventually. And now, let me go quickly through the dynamics part. Which is actually the main part of my talk, because half of the talk was the introduction, intentionally. And so I want to consider sort of a classical physics, very standard physics thing. If you see something that moves, you want to develop a linear response theory. Okay, so there are some forces which act inside chromatin, how it flows. Let's see what linear, elementary, naive linear response theory will tell us. So linear response theory means simply that you have some force and you observe some variable, and this, the only thing that you assume two things. You assume that it's linear and you assume that there is causality. Only the previous history of your system affects you. Okay, so there are two types of forces in action. There is thermal force, some thermal noise, and there is some activity, various sorts of activity. And the result, whatever variable x you want to choose, the result of it, of this type of study would tell you that fluctuations of your variable are proportional to temperature if it is driven by thermal forces, which is not surprising, but it's called fluctuation dissipation theorem. It's a pompous name, but it just says that the fluctuations are proportional to temperature. And if you have active drive, then fluctuations are proportional to active drive. There is a coefficient which is susceptibility of generalized susceptibility and so on. I want to point out that general rule is that the more active you drive, more stronger fluctuations. On the other hand, we know that from many everyday experiences, as well as from some of the talks before me, we know that some of active processes actually are designed somehow to quiet fluctuations, to reduce fluctuation, to dampen fluctuation. So notice that this theory does not give you any clue. And to the best of my knowledge, there are no theories which answer this question, although we have some ideas how to do it, but they are not ready yet to be discussed. So I will therefore continue with this limitation. I will continue along the lines of linear response, and I will look at chromatin as a two-fluid object. So two fluids means there is chromatin itself and there is solvent. So when you want to condense part of the chromatin to increase volume fraction of chromatin in 1/2, you have to squeeze liquid outside, and that's basically what we are talking about. So therefore, the first thing to do is to write stress developed in this chromatin polymeric material, and that there is standard physics how to do it, except now we need to look at this generalized elastic modulus, viscoelastic modulus, something that Professor Spakovich was already referring to. But we need to do it for a specific object, which was not looked at before in polymer physics, because nobody was considering this territorial organization of polymer chains, and you know that chromosomes occupy territories. So therefore, what you need to do, first of all, you need to think that your viscosity, what sits here, if you compare it to normal Stokes equation, what sits here is basically viscosity. Okay, so maybe it's viscosity. Well, it's known that for viscoelastic materials, viscosity will depend on frequency. Okay, but here it depends more than on frequency because it depends also on the length scale. Why it depends on the length scale? If you imagine doing a microreology experiment, if you imagine inserting a particle in your chromatin and watching how it undergoes random motion, then you hope to extract this generalized viscosity from essentially the Stokes-Einstein formula, and there is Rp, which is radius of your particle. Rp stands for particle radius. So this essentially is your mean square displacement. Forget about the technical mathematical details. It's Fourier, not Fourier transform, but Laplace transform, because it's more stable. Doesn't matter. But importantly, there is particle size. And accordingly, the quantity that is here, generalized viscosity or generalized modulus, depends on the spatial scale. And when you are dealing with territorial polymer, the most interesting part is when wave number belongs to one territory. So here, at larger Q, you are at the scale which is much smaller than territory. It's somewhere where you look at small pieces of your polymer. Here, in this region, you are looking at the scale much larger than territory. So this is a new interesting region, and here are the results of theoretical study of these two real and imaginary parts of your generalized modulus. And notice how a real part, which describes elasticity, how rapidly it decays with the wave number. It's Q to minus 11. I don't remember seeing power minus 11. Oh, very good. I actually thought that I have less. Thank you. Okay, that's also possible. So it's very rapidly decaying. So what is the physical meaning of it? Physical meaning of it is very simple. Imagine that you take a rope, which is sort of representative of a polymer chain. You take a rope like this, and you can imagine that some weight hangs on it. Imagine now that you crumple this rope, okay? And now try to hang this object on the crumpled rope. It will not hang. It will unwind. That means the elasticity is very small, and that is what we observed here. I will not go into details why crumpled rope is related to, but it is related to territoriality, which we observed here. Okay, so that's the consequence. Now I want to emphasize that this is fundamental difference of this situation with territorial polymers when new non-trivial regime comes at intermediate wave vector and intermediate frequency, which corresponds to probing inside territory, and how it is different from the situation when, for instance, you have hydrodynamic interactions. I didn't say anything about hydrodynamic interactions. Hydrodynamic interactions are important outside of this diagram because hydrodynamic interactions are screened, as I told you, on large distances, and therefore they only exist at very large Q, at small distances. Between pieces of polymers, they are important, and here in the internal part of this diagram, they are not important. Similarly, the issue of semi-flexible, these polymers are semi-flexible. And there is beautiful physics, Fred McIntosh, I should say, Professor McIntosh, developed beautiful physics of semi-flexible polymers. This semi-flexibility is is in this part, outside. And our territoriality is in the internal part. Okay, so what are the consequences of it? Several years ago, Alexandra Zidovskaya and Itzhak Rabin and Robin Grunschma developed hydrodynamic theory based on similar arguments. And looking at this two-fluid model and so on, I will skip all the details, but I will tell you that, in fact, what we can do now is we can add one more possible source of activity in that hydrodynamic theory, which is indicated by the force here. So what this equation means, it is basically 1 minute. Super. It is basically force balance of the solvent. And there is a possibility that there is an extra force which acts on the solvent from some active source. The only rule is that there is the same force with the opposite sign acting on the polymer. That means if this table is a polymer and I am an active motor, then I can push it. But simultaneously, I have push on the solvent, which in this case is the floor. Alexandra mentioned this to you, and you saw these pictures. And what I'm now telling you is that there is extra term here, extra term, which is another source of force dipoles, which can undergo pneumatic ordering. And I think, so there are not two, but more types of these active forces. And there is this pneumatic ordering, which is series delight and so on. And I will finish on this point. I will skip completely the nonlinear part and show you finally main pictures of this talk. And for your entertainment, a beautiful poetry from James Maxwell, 19th century. This is from postcard that he sent to Tate. Very interesting poem. I encourage you to read. Thank you.
James, when to answer.
This is very nice. I was sort of curious in the beginning when you brought the slip knots, come to my past, slip knots in proteins, did a lot of work that with Joanna. Now, if you look at the final structure of chromatin, we always say there are very few.
What do you mean final? Final is when we die. Then it's final.
No. We say that there are very few knots or no knots. Do you have more knots or more slip knots? What's your feeling for in the end of it?
I do not know. I do not know. It's a very good question, but I don't know the answer. I wish I knew, but it's a difficult question to answer.
Yeah, I think that your points about the likelihood that we'll be able to sort out slip knots in chromatin are really absolutely correct, and it's a really interesting direction. I'm curious, do you know what the state of characterization and classification for slip knots is right now? Is there a good classification system that one can use for asking questions like that?
You ask me a dangerous question. You ask me if there is a good classification. You ask me to classify it as good or bad. I do not know. In general, I would say it depends on what you want to do. For some purposes, it's good enough. For purposes of, let's say, computing Let me answer this way. Here is the question to which I want to know the answer, but I don't. I don't know if you know how to knit, but very elementary set of knitting operations involve two types of loops from front or from back, basically, roughly speaking. And accordingly, any sweater is basically an Ising model because every loop can be in principle in two sides. If you do it in paramagnetic sweater, it's very ugly. But ferromagnetic sweater, which is ordered, is more nice. So in general, the question is, what is the entropy of knitting? And accordingly, since I don't know this question, I don't know how to classify all sorts of knittings.
Thanks.
All sorts of sweaters.
Okay, Andy.
I can wait too. Thank you. That was really interesting. What I'm trying to understand is, normally when you take, your linear response, right, and then you have the fluctuation dissipation theorem, your frequency dependent, I guess you had a chi, right, is tied directly to that. But your pneumatic force, what is the spectrum that you use for that pneumatic force correlation function? Because that can affect a lot of things. That can affect the sort of equilibrium structure on a local scale. That can affect, the probability distribution for a lot of things.
Thank you. It's a very good question in a different sense, in the sense that I know the answer. So this is pneumatic order of an unusual sort. Normally, pneumatic order comes, as we know from Onsager, or I don't know who was the first, probably Onsager. Normally, pneumatic order arises because of asymmetric interactions or asymmetric shapes of molecules. Here, nothing like that. It's purely non-equilibrium situation in which maybe there is some biological reason for pneumatic order, which we don't know, but which we indirectly hypothesize because we observe, as Alexandra Zidovska, I should say Professor Zidovska showed yesterday, we observed these large-scale flows. From that, we indirectly hypothesize that there is pneumatic order. That's one possibility. Another possibility is that the flow itself generates ordering. And by the way, I have to emphasize, the flow should facilitate ordering of what? Ordering of force dipoles which cause the flow, not fibers of chromatin, not necessarily fibers of chromatin. Okay, especially this new active forces gamma, they can very easily align, more easily align than the ones which are associated with the fibers. So therefore, there is no intrinsically linear response contribution to generalized susceptibility due to pneumatic order.
So I'm going to suggest that we thank our speaker again.
Thank you.
And our final speaker of the afternoon has postponed until tomorrow, so we are only an hour over schedule. So they are never going to let me do this again, which I did on purpose. So Kristan, wherever you are. Anyway, so why don't we thank the speakers for today? I mean, it was a fascinating day, so thank everyone again. And we'll see you all tomorrow morning.